Good afternoon and welcome to the third How TrueAllele Works this week on Kinship, Paternity, and Missing Persons. I'm Dr. Mark Perlin from Cybergenetics, and today we'll be talking about kinship. So the task in kinship analysis with DNA is to infer genotypes and then match them. The main tool that we have at our disposal is Bayes' theorem, which we'll see again in this webinar. And the main data that we're working with are the genotypes of the family members along with their pedigree organization. So as you recall, Bayes' theorem is a way of starting with prior information, shown in brown on the top right, combining it with explanations of data using probability, which is a likelihood, shown in green, and then moving to the top left, that's how we obtain a posterior distribution. The posterior probability of some event is proportional to the likelihood times the prior. And we see in the center of the screen this idea expanded a little more mathematical notation. On the left in blue, we have that the probability of some unknown or uncertain quantity, capital X, or random variable that can assume multiple values, the probability of capital X, the variable, assuming one of those values, little x, conditioned on the data, is proportional to, in green, the likelihood, the probability of that data, conditioned on that event occurring, that the variable x has that value, little x, times the prior probability, shown in brown, of the event that variable x assumes the value little x. So we'll be seeing this a lot. Posterior is proportional to likelihood times prior. This is a family relationship that you're familiar with from genetics. That's a pedigree. And this is the main template we'll be using for most of the presentation and examples. At the top of the pedigree, we have a father indicated in capital F and a mother indicated capital M. The fact that these circles and squares indicating females and males respectively are filled in indicate that they're known quantities. Now their offspring is a person, capital X. That's the person whose genotype we're trying to infer. That person has a spouse indicated with a capital S, and their offspring are 3 children, indicated by C or C1, C2, and C3. So that's the pedigree we're starting with, and those are the family relationships. The task is to determine the random quantity X, which is the genotype of the person in the pedigree. So if we're going to use Bayes' theorem, we're going to have to use priors and likelihoods in order to obtain posterior probabilities of genotypes. So let's take a look at what a prior probability here means for a genotype. That's how a variable is affected by other conditions. So in this case, the probability of that variable X, the genotype of this person, say at a locus, assumes a particular value or allele pair little x, is conditioned on background information. And that's the flow of genetic information from that person's father and mother. And in this example, the father has an allele pair AA, shown in blue, and the mother has an allele pair AB. Okay, so how is this prior knowledge about this individual, the probability of this person, affected by other variables flowing in? As you remember from college genetics, we can draw a Punnett square to address a question like this and work out the probabilities of different genotypes. So shown on the bottom left in brown, the probability that the person's genotype, capital X, has some value of allele pair little x, conditioned on, in blue, the father having an AA, and in red, the mother having a BB. Moving over to the Punnett square on the right, we see the father's genotype in blue is an AA, the mother's is a BC in red, and by combining the rows and columns, we obtain allele pairs, AB, AB, AC, and AC. And just by adding up these possible events, we see on the bottom right that the random variable of the person's genotype X assumes the value AB with probability 1/2 and assumes the allele pair value AC with probability 1/2. So that's the flow of information, and now that's the starting point for what has influenced the random variable X. The likelihood asks the other question. It asks, how does the variable influence other variables? How does it affect other variables? And shown in green, we have the probability of the child's genotype conditioned on the person's random variable X, assuming any number of allele pair values, little x, and the spouse, shown in red. That is the likelihood. As we put in different values for X, the father, then we'll get different probabilities of how that father, together with the mother, influences the genotype of the child. And so let's look at an example. In this case, we have that suppose that the spouse's genotype is a BB, pair of alleles, and that's a known fact. And the child's genotype, shown in blue, is AB. That's indicated on the left side of the probability conditional and also on the bottom of the pedigree. Now the question is, what possible allele pairs can the unknown person's genotype have that can have produced the child's genotype together with the spouse's genotype? Well, looking all the way on the right, we see that if the spouse's genotype is a BB in red and the child's is an AB in blue, then that child's B allele must have come from the BB homozygous spouse. So then the question is, looking over on the left of the pedigree, is where did the child get the A allele from? Well, it must have come from the father, shown in green, that person. Shown underneath are different possibilities. AA means a homozygote. A not A means AB or AC or AD or any heterozygote that includes an A. And at the bottom we see A bar, which means neither allele is an A. And over on the left, we can look at the likelihoods of these. If the person has an AA allele pair and the spouse has a BB allele pair, then the chance the child has an AB is 1. So the likelihood is 1 for X having an AA. If a person has a heterozygote that includes an A and a not A, then there's a 50-50 chance that will produce that flow of information to the child having an AB genotype. So the probability that C equals AB, the child has an AB, given that the father has an A and another allele and the mother has a B and a B, that's 1/2. And the last case is if the father doesn't have an A allele at all, then the chance, assuming no mutation or other events, of the child having an AB genotype is 0, because there's no way the child could have gotten that A allele. So this is the basic concept of likelihood, that we're asking, how does a person's genotype influence the genotypes of their offspring? This is a very standard concept in genetics that's been around for about 100 years. Now that we have a likelihood and a prior, we can combine them in order to produce a posterior probability, and this is what we're going to do. Suppose we have a person with an unknown genotype labeled in the center of the pedigree, capital X, that's the random variable, and the father and mother's genotype are known, as shown here, as an AA in brown and a BC in purple. So there's data coming in and influencing the prior value of X. And then there's also a child indicated as C, and that person X and their spouse S, with the allele pair BB shown in red, have influenced the allele pair value AB of their child. Putting that all together, the parents flowing into the person provide a prior probability, shown as the prior that x equals x, given the father and the mother, and the person and their spouse influencing the child provide a likelihood, shown in green in the top center, of the probability of the child, given that the genotype of x is some value together with their spouse. And the posterior probability, shown on the top left, the probability that the genotype value is x, given all that information, the genotypes of the child, the spouse, the father, and the mother, that will be the posterior probability. So let's calculate that. If we look on the bottom right, we have the prior probability in brown of the genotype X, assuming a value X, given that the father is an AA and the mother is a BC. But we already solved that problem with our Punnett square, and on the bottom right of this slide, we see that the probability then is that 1/2 that X is an AB, 1/2 that X is an AC, and 0 that it's anything else. So we've already restricted the situation that the genotype must be an AB or an AC with equal probability. And now, on the bottom row, moving over to the left part, we have the likelihood part of the equation. And here we have the probability in green that the child in blue, AB genotype, given different values of X, and the spouse is a BB allele pair, we ask what are the possible values of probability once we put in those values of AB and AC. And what we saw in looking at the likelihood function 2 slides back is that for a heterozygote that contains an A, that A bar situation, which is both AB and AC, shown all the way on the left, that has a likelihood of 1/2. And so that means that whether the genotype is an AB or an AC, which has equal prior probability, it also has equal likelihood. And so we don't have to do a lot of math. The likelihood and the prior don't change those probabilities up or down. And so now we can look at in the center of the slide that a person's genotype value X can be an AB with probability 1/2 or an AC with probability 1/2. And that's the posterior probability that capital X assumes one of these values, the unknown genotype, conditioned on all the other pedigree members. So now, by looking at the whole pedigree with all this information, we can calculate the posterior probability of the genotype of this individual at this locus. But we don't just want to calculate this person's genotype. We want to make comparisons. And if we've inferred through kinship information that a person's genotype is an AB or an AC, each with probability 1/2, we want to compare with another person, a suspect or an alleged person for some condition, indicated here as A for the alleged person, and suppose that individual in green has an allele pair of AB. Well, we can make a comparison. We can see that it's certainly possible, but that's not enough. We really want to work out what the strength of match is and not just say, well, it's possible. And to do that, Bayes' theorem comes in a second time. We used Bayes' theorem the first time in order to infer the genotype of an individual, say a missing person in a pedigree. And now we want to find support for a hypothesis. In this case, a reasonable hypothesis might be that the missing and reference persons are the same individual. The likelihood ratio, indicated by LR in the center of the screen, as we discussed in the first webinar, is the odds of this hypothesis, H, given all the data, which here is the kinship information, of the different genotypes of the relatives, divided by the odds of a hypothesis H before we ever saw the data. And then by applying Bayes' theorem and doing some rearrangements, as we've already gone through in a previous talk, we end up with a ratio of probabilities. It's the ratio of the posterior genotype probability to the prior probability evaluated at this individual's allele pair AB. So the last line is the probability that the unknown genotype X has the value AB conditioned on the pedigree information of the child, the spouse, the father, or the mother, divided by the probability of this person having an AB genotype prior to having seen any data. This is actually a very old idea if you consider the likelihood ratio to have been developed around 1945, 1948. This paper by S. and Muller on paternity testing in blood group analysis had described the likelihood ratio concept as taking posterior to prior genotype probability ratios 10 years before. So let's do the calculation of the match strength. If the likelihood ratio, as shown on the first line, is the posterior probability that X, the genotype X has the value AB, divided by the prior value that it has the value AB, well, we know what these values are. The posterior probability, shown in blue, we had calculated to be 1/2. It's right there in the center of the genotype probability slide. AB has 1/2 probability. And what's the probability that a person has an AB heterozygote genotype? Well, in brown in the second line in the denominator, that's just probability of a heterozygote, 2 times the probability of A times the probability of B, based on the allele frequencies in the population. So putting that all together, in this particular case, with these particular genotype values on this pedigree with those known individuals, the likelihood ratio at this one locus is 1/4 PA PB. Okay, so that's calculation of how we arrive at a strength of match by first inferring a genotype probability, and then from kinship data, and then using that in the likelihood ratio. Next, I'd like to talk about paternity, which follows these general principles. Here, the task is to determine the genotype of an unknown biological father, indicated by the variable X, given that we know the spouse information, S in red, and the child's genotype, shown as C in the square box. The parents are typically not known, so we don't have that information. Instead, we use population data to stand in for the parents. So now we have an inference question. The first step will be to infer a genotype for X as a probability distribution, and then the next step will be to make a comparison with an alleged father in order to compute a likelihood ratio. So doing this on some actual data on the 13 core CODIS loci, looking at D7, this is one locus where in the top half we're showing the paternity genotype for individual X. This is what it looks like out of the 100 possible allele pairs. The probability has been reduced down to these 8. And that's in the top half. Now, do we think there's information here? Well, the bottom picture shows the same blue probability distribution, the posterior distribution, after having seen the spouse and the child as a likelihood function together with a population as a prior. But now we're showing it relative to the prior distribution of the population in brown. And what we can see is that the brown bars, which give the probability distribution of a random person in a Caucasian population, are different than the blue bars, which tell us what the genotype probability is at this D7 locus after we've seen the pedigree data. So if there are differences like this at every locus, we would expect that there would be some information. The way we extract that information is we make a comparison now with an alleged father A. So previously, we just had a paternity genotype as a probability distribution. We didn't have a particular suspect or alleged father to compare with. Now we want to make a comparison. It'll be of genotypes. The genotypes at every locus of the alleged father A, shown in green on the left, and the genotype of the inferred biological father from kinship information, who has the genotype of the individual who fathered this child together with the spouse. So to do that, we go back to our picture of the blue posterior distribution at this D7 locus and the brown prior distribution. And the green bar is now showing the probability of the alleged father. He has a 10-10 with probability 1, whereas the biological father inferred from kinship in blue has a diffuse probability distribution with not all the probability concentrated in one place. By comparing the ratio of the blue bar, the posterior distribution of X, the unknown genotype at this locus, relative to brown, which is the prior probability of an individual before we looked at the data, then we are essentially just looking at this formula of posterior to prior, which we'd evaluated in a simple case. We're applying it again here, but now visually we see blue height divided by brown height, posterior to prior, at the suspect's genotype 10-10 gives a ratio of around 3.5. That's the likelihood ratio, which is the same as the paternity index. And the log of that likelihood ratio of 3.28 is 0.52. Now, doing this at all the loci, we see in this interface that every row is showing the posterior distribution for the locus as a blue bar chart, the prior distribution as a brown bar chart, and the suspect's genotype of where we're going to take that ratio indicated with a green bar. That's on the left, and then moving over to the right, those ratios are taken of blue to brown, posterior inferred kinship relative to population prior, and the logarithms are taken. And on the right, we see bars to the right that in blue that indicate support for the hypothesis that they're the same individual. There's also a little red bar at D8 that indicates really no support either way. Adding up all of those weights of evidence at each locus gives us the total weight of evidence, or the log likelihood ratio, for this comparison, and that number is 5.41. When you take 10 to that power, you obtain a likelihood ratio of around 250,000. So that is the strength of match for a comparison in this paternity, or a paternity index that tells us to what extent this alleged father is the biological father and that they're one and the same individual. Now that we have paternity under our belt and some other kinship concepts, let's take a look at a maternity question that happened recently in a TrueAllele user lab. In this case, there was a child who was deceased, an infant, and there was a question as to who was actually the mother of this child. And so there were a set, here I'm going to indicate by 6, but there was more than one alleged mother. And the question here was, what was the relationship between this child and these alleged mothers? And the way to solve this problem is by, on the left, having a pedigree, the kinship information, and asking what is the inferred genotype of the biological mother of this child. So what is the probability distribution, or the genotype of the unknown variable X? What is the genotype of the biological mother? Given we know she comes from the population and her likelihood function is constrained to the genotype C of the child. And then once we know her genotype, then a comparison can be made with the alleged mothers. So this is what the biological mother's genotype looks like for the unknown genotype X. I'm showing it here for 5 loci, D7, D8, FGA, O1, and TPOX. The main thing you see here is that the probabilities, the heights of the bars, of the posterior inferred biological mother distribution for X in blue is different at each locus from the prior population, the random population shown in brown. And since there's a difference between the blue histograms and the brown histograms at every locus, that indicates there's information here. Now, the information may be exclusionary or inclusionary for an individual person, but there is information present for identification. And so in this case, when we make the comparison of the inferred biological mother's genotype from the kinship data of the child relative to the 6 individuals, A1, A2, A3, A4, A5, and A6, what's shown on the right is the total log likelihood ratio. And here we see that individual A1 has a log LR of over 1,000. 3.6, the likelihood ratio is over 1,000, and the log LR is 3.64, which is an inclusionary value, which lends considerable support to her being the mother of this deceased child. The other individuals, when their genotypes are compared against the inferred biological mother, have exclusionary values shown in red, and they have negative log likelihood ratios, here ranging from around -4, which is 1 in 10,000, down to -7, which is 1 in 10 million. So this sort of inference problem, by inferring the mother's genotype from kinship information, is able to answer the question as to which of these women is actually the biological mother. We'll now take a look at a missing person example, and what I'm going to do is just show you a set of data of how kinship information can be derived and how by changing the number of children that are used, whether parents are used, whether a spouse are used, the amount of information changes as well. Generally, with more data, there's more identification information. Shown on the left is a family pedigree. X is the unknown missing person, and this person has 3 children, C1, C2, and C3. Shown on the right is the log likelihood ratio, and the 3 bars represent whether 1 child was used, the first child, whether 2 children were used, 1 and 2, or whether 3 children were used, child 1, child 2, and child 3. And we see that as more children are used to infer this unknown missing person's genotype, we get increasingly higher match statistics when comparison is made with the correct missing person, with the correct individual. The numbers go from 3.5 and with 1 child, and then move up to 7 when there's 2 or 3 children. Now, what happens when we add a spouse? When a spouse is added, there's more likelihood information. Without the spouse, we only have information from 1 parent, but with the spouse, we have information from both the unknown person's position X and their parents, which is in this case is the population, together with the spouse information, and that gives a much more definite likelihood function for inferring the children, and therefore, when you put it all together, there's more data for determining the genotype X, what is the genotype distribution of the missing person. Whereas before, without the spouse, the numbers range from 3.5 to 7. Now, as we move in a series from top to bottom on the right, considering 1, 2, or 3 children together, the numbers are moving from 5.5 up to 10. So considering the spouse strengthens the likelihood function for inferring the unknown person X. Similarly, if we have parents and not a spouse, and we look at the series with using more children, the father and the mother puts considerable constraints on what the genotypes of the unknown person X can be as prior information, and then the children add more likelihood constraints because they're affected by the genotype of person X. And here, the series, as we go from just the first child to then the first and second child and all 3 children, now the numbers are moving as log likelihood ratios from 9.5 up to 11.5. So the parents are a very good constraint. The more data you have, the more constraints you have that restrict the possibilities of what a genotype can be or what their probabilities can be, and that thus sharpen the genotype and strengthen the likelihood ratio. Finally, if you have the parents and all the children and the spouse, it's the most information you can have. So it's the whole family trying to help infer that genotype of missing person X. So with even only one child, the father, the mother, the spouse, and one child, in that first row on the right, you're already up to 11.5 log units. That is, the likelihood ratio is up to almost 1 trillion. And if you add a few more children, the second child and the last bar is showing the first, second, and third child, you're now up to about 10 trillion with 13 log units. And so it's a general principle of statistics that the more data you have, the more information you have relative to using less data. For the last example today, I'd like to talk about how you can look at DNA mixtures together with kinship in some problems that come up in casework. So consider that you have a DNA mixture. This is a 70-30 mixture, and the major contributor maybe is a known victim. And the question is, what can we say about the minor contributor, individual who we don't know yet, but we're trying to find? It may be the case that by searching with this minor contributor on a database, we may come up with a relative of a potential suspect. For example, as with the Grim Sleeper case, a father was found, indicated as F here, as the father, of an individual who might have been a potential perpetrator. So now we have mixture data on the left, we have kinship data on the right, we know who the father is. What are we going to do to ask a question about this information and determine to what extent is this unknown person X, the son of the father, possibly a contributor to this mixture? Well, the approach is to infer genotypes. From the mixture, one can separate out that mixture with TrueAllele and infer the minor 30% contributor. And similarly, with kinship, you can use a method such as TrueAllele to infer the unknown person X's genotype as a probability distribution. And now you have the genotype from one contributor, the minor contributor to the mixture, and the genotype from a family, the unknown person X. And now a genotype to genotype comparison can be made. So this is what it looks like. So in blue, we're talking about the minor contributor here at locus CSF. And on the bottom of the chart, we've listed about 10 allele pairs. The y-axis is showing the probability. And within any color, the probabilities add up to 1. The blue bars in the center are the probability distribution of that separated minor contributor, separated, a genotype separated out from the mixture. And that's where that person's probability lies. In green, we're seeing the kinship inferred son. That's the genotype of one contributor in this family, one member of this family, and there is their genotype. And then in brown, we see the genotype of a random person. What's the chance that a person at CSF would have any of these different allele pairs if they were randomly drawn from the population? But by having 3 contributor genotypes, one from a minor contributor to a mixture, another that's a kinship inferred individual, and the third from the population, we can work out what the likelihood ratio is. We can work out a contributor genotype match statistic. In this case, the likelihood ratio is around 40,000, and the log LR is about 4.5. The way we can combine these 3 genotypes, the posterior distribution of the mixture in blue based on the mixture data, the posterior distribution from the kinship data shown in green, and the population data shown in brown, summed over all possibilities, is the same likelihood ratio formula that we saw a few months ago, which is the general way to combine uncertain genotypes, whatever their source, mixtures, kinship, populations, and put them together in one formula to arrive at a measure of information, the log LR, in this case about 4.6, that tells us what the support is for the hypothesis that these are the same individual. We also made a comparison shown on the right in red with 10 random individuals comparing the mixture to these individuals to obtain a likelihood ratio for this 30% contributor. And as you can see, they're largely exclusionary, or actually very large and exclusionary, with numbers ranging from -18, which is 1 over a billion billion, past -24, which is 1 over a trillion trillion. This is another way in which the idea of using separated genotypes, whatever their source, mixtures, kinship, databases, populations, can all be combined to obtain a likelihood ratio match statistic. So thank you for your attendance at this part 3, How TrueAllele Works, on kinship, paternity, and missing persons. The next month's How TrueAllele Works will be on genotype databases and DNA investigation on the 15th of January next month. You can sign up for it by the end of today. It should be posted on our webinar page. The URL is given here. Today's webinar will also be posted on the website for webinars for people who may not have had a chance to attend. So thank you again, and at this point I'll start taking questions.